concerning the usage of the SIESTA code is extremely varied. I mean, in the moment you can put lots of atoms into a box, then there's quite a lot of simulations within the context of physics, chemistry, material science, bio context, geo, nano, even engineering. It is hard to follow what people are doing in the community, since we have of the order of 14,000 paper sightings the SIESTA core papers, around 1,000 a year. So you can imagine that there's quite a lot of variety in these things. Let me just illustrate it with some different examples close to the kinds of things we do. And here in the materials context, for instance, here I show a nice picture of large-scale material simulations of a ferroelectric paraelectric superlattice, in which you can see vortices of polarization within the ferroelectric, which is it was published a few years ago, and this involves several thousand atoms in the calculations, and it involves second principles for the simulations. So the bio context has been very much at the heart of the early SIESTA development from the beginning, and the structure and electronic structure calculations of DNA at a full double strand of DNA was one of the early results of us ourselves within SIESTA, with SIESTA, as you can show there, but it has been applied to many other things. Here's another example here below, which is a pillin protein in wet conditions, and here there is electrostatics. That's an electrostatic map, but is a situation in which we have a natural evolved nanoelectric wire, which some strange bacteria are using to feed themselves. And so electronics is very important there, as well as the electrostatics shown here. So there were SIESTA calculations, again, with, in this case, it was of the order of 4,500 atoms. And other completely different, but also interesting kind of example is this one in which we're looking at electronic transport. Both Pablo and Nick are going to talk about these things. This, let me just illustrate it. This is a 4-point contact, and you have electronic transport in this quite demanding situation, relatively recent calculation. So a little bit closer to my own work, we're doing very far from equilibrium simulations using time-dependent DFT in a similar way that you would do time-dependent Schrödinger equation. That would be the equivalent Kohn-Sham equation, but it is the time-dependent like. And what we're doing is shooting projectiles through solids, which generate very large energy transfer. So we're not talking about subtle energetics here. We're talking about many electron volts per angstrom along the trajectory. So we put a projectile into a simulation box and we kick it, and it moves across and generates all sorts of havoc. And this is what you're seeing here in this illustration of protons and germanium. And through that, we have been learning quite a lot of things related to this very highly non-equilibrium process. In particular, for instance, one can see things like that. This is the actually dissipation of this proton due to the electron excitations for protons in gold and alpha particles in gold. This is a comparison theory of experiment of the kind you're very used to and the kind of accuracy you're very used to with density functional theory. But in this case is a genuinely far from equilibrium quantity, of which you don't see so many in the first principles context. So that has been quite pioneering as well.